In the afternoon session, we have 4 talks. The first talk is an invited talk, followed by 3 contributed talks. I guess all the 4 talks are on the experiment. So the first talk is by Professor Chen from University of Science and Technology of China. So he will talk about large-scale quantum network in China. So let's welcome.
Thank you, people. It's good afternoon, everyone. It's great pleasure to be here, and as I'm also kind of half of the local. I'm not a local organizer, but I'm local. So welcome to Shanghai, and I hope you had a delightful stay. And I will have. The conference is like half past, and the next half time. I hope you still enjoy the conference. And I slightly modify my talk. The title of my talk, it's large-scale quantum network from intercity to intercity to global. And yeah, I think as it's quantum QCrypt, so I think I cut a lot of background introduction, but just to start, still, nowadays we have a lot of information. And in a period of time, or in a unit time, information created basically are it's exponentially increased, which means we have more and more security problems. So it can be secure everywhere. It can be in the data center, or it can be during the information exchange. And the normal way is that is of course the encryption. And so classically, we have different methods of encryption. Say symmetric encryption, we have AES, IDEA, and RC6, and asymmetric encryption of ISA, and so on. And for the symmetric encryption is more efficient, and but the thing is, so normally it requires a seed key. Basically, normally what we do is we use ISA to exchange the keys. But for more secure ways, one-time pad, but then the key exchange will be a problem, because for ISA it's really also not so efficient. And also, for classically, we know that ISA 512 was cracked in 1999, 768 was cracked in 2000, and 1024 was, so far was not announced cracked, but actually in 2011, NIST already claimed that it should be not used from end of 2013. And actually, since 2015, they already suggest to use 3072 for the top secret. And also, we know all classical symmetric encryption can be cracked by quantum Shor's algorithm. So, after the celebrated BB84 was proposed, and there's a lot of, I skipped it's a little bit jump since I cut some background slides, but still. So after the first demonstration was done in a table with 32 centimeter, and people try to, if you want to use it, of course you want to use, at least one would say about 100 kilometers. For instance, let's say 10 kilometers, if you separate by 10 kilometers, you just can't go there, no? And, since 2005, it's the distance already exceeded 100 kilometers, but there's some severe problem. One is from source, one is from detectors. Actually, before 2005, all the experiment was done. The secure distance is only about 5 to 10 kilometers because of the photon number splitting attack due to the imperfect source. And also, we have the imperfect single photon detectors. And in 2005, 2 groups proposed the solution for the source, the so-called decoy state method. Basically, instead of send a fixed intensity of the pulse, it randomizes the intensity and randomly send P1 and P2 and vacuum, and to check, it's so-called request to check whether there's an eavesdrop in between. And with this method, finally, in 2007, people can extend the really provable secure distance to 100 kilometers. And for the that's the imperfection for the source. And for detectors, for instance, the next loophole is caused by the imperfect single photon detector, especially for example, if one use the strong light to blind the detector, then when eavesdrop when it sends the, let's say, threshold is 1.6 I, and only when it beyond the threshold, the detector will respond, which means it will only respond when the measurement bases are exactly same as eavesdrop. So to solve the problem, also again, Ho-Kwang proposed the measurement device independent quantum key distribution, and basically one send a single photon here, then perform burst measurement. And since the eavesdrop, this measurement device can even controlled by eavesdrop, because it can only it only knows whether the input photon is same or orthogonal, and no original information from others. And the first experiment was done in 2013, and then extended with 50 kilometers and extend 200 kilometers. And this was done in table, and a field test was also performed later with realistic fibers. And having solved these two security loopholes, QCrypt finally become a variable technology under realistic conditions. In the past 10 years, we have realized a large-scale metropolitan quantum communication networks with application, bank transfer, and so on in China, in Europe, in Japan. And the first scaled metropolitan network was done in Hefei with 46 nodes in 2012, actually. And so this was the map of Hefei. We have 46 nodes, and it's actually like fourth generation of this QCrypt device. And if we go back to the first experiment in 2007, it contains the whole experimental table and the control devices, and the bit rate is about 8 bits at 100 kilometers. And now, so the second generation is like a whole rack, and then in 2010 it's half rack, and now we have its 4U rack with standard generation, and it can support 4-channel in parallel. And the bit rate is about 10 kilobytes per 100 kilometers, so its size decrease 10 times, bit rate increase 1,000 times. Actually, if you count the price for 1 kilobyte, price cost for the final key, it was decreased like something like 1 million times. So, but the things, as I said, so in the beginning, the symmetric encryption has the advantage of the harder to encrypt, but then the problem is when the key it requires the seed key exchange, so that it will have cause security problem. Also, using ISA to exchange the key, actually, if you use ISA 3072, it's really slow. And but now we have, as I said, so we have 10 kilobytes at 100 kilometers, which is still, I mean, for the one-time pad, it would be very, it's not so useful. I mean, normally we have data are at a gigabyte or even higher rate. So the solution is in combined with classical symmetric encryption. So we use quantum key distribution to distribute the seed key and encrypt by the, let's say, AES or SM4. And actually in 2007, in DARPA quantum network testbed, they already proposed that this is an important result. It buys time for further improvement while denying an enemy break. And but at that time, they say they claim that they predict that the DH will be break in 2015, which is fortunately is not the case, but still I think you don't know. I mean, so this is the topology of our Hefei network. So it has the loop shape and then the star expanded. So the nice thing for this is that to expand is very easy. You just find one point and connect to the loop. And also the nice thing for the loop connection is if let's say this one is break, you can quickly switch to the reverse loop. And we also have three type of users. And one is the relay, one calls the general users, and the VIP users here means one can use optical switch that without a trustful relay, so they can directly communicate, distribute the keys. And also, this is newly launched Jinan network last year. It covers the whole Jinan city for the government office, providing quantum encrypted audio call and video conference, and it has 32 nodes and in total like 242 officer users. So again, the general ask question is: so you have multiplayer networks, how to expand to the long distance? I mean, so for you with the measurement device independent QKT, with the ultra low loss fibers. One in laboratory, one can do experiment for 400 kilometers, and with free space before we perform the teleportation at 100 kilometers, and also in Vienna groups also 100 kilometers. But if you want to go further directions, the problem with fibers, the main problem will be the huge photon loss because it's really increase exponentially with the distance. So I directly quote Nicholas Jason's paper that for 1,000 kilometers conventional fiber, even with a perfect 10 gigahertz photon source, perfect detector, you get 0.3 photon per century. So basically, there are two main solutions: satellite-based and quantum repeater. So the first solution is quantum repeater. I'm not going to details for quantum repeater. Basically, it's divided to distant location to few segments. Then with entanglement swapping, it connects the whole distance, and with purification, it gets purify the state, and then you do the QKT. And the main technical problem here is the quantum memory. So this means it's still practically challenging. So far the best quantum memory is, so in 2012 is here, and the year before last, we finally reached here, which is if you don't care about how much you spend, you finally are able to create keys at 2.2 hertz rate at 500 kilometers. So this is so far the best memory result. So both taking care about the quantum, the memory lifetime and the retrieval efficiency. So of course, then it's still practically still challenging. Another approach is the trustable relay approach. We know that, I mean, classically, what we do is when we send a file, it's not done to work. So we can make someone in between to here. So basically, the idea is, I mean, the Alice created the key with the relay, and then the relay encrypted the key he created with Bob and send it to Bob, and then Alice and Bob can share. But then, of course, the only thing here is the one in between has to be honest. So we know this guy is honest, but we don't know others. And but you know, when the bank, so in 2012, actually, after we created the Hefei network, the banks comes to us. They're asking whether you are able to perform the long distance, because in China, the banks really, there's a lot of data to be encrypted, to be sent the key management behavior in China or whatever. So they are at very low. I mean, the key, the seed key update rate is officially two times per year. And most of the time, they actually don't have it once a month, or once a year, actually, less than once a year, so the bank. Then the bank comes to us, we tell them, okay, so we can do intra-city, but intercity we have the problem. So we have this approach. But they are really excited because they say, so, okay, because they say you relax the whole leakage of the possibility of leak the whole line to a few certain points. I mean, with certain points, we can just guide it very. So actually, really encouraged by the users, we start to think about to build the backbone. So the first solution were released from quantum repeater to classical repeater, basically the trustable relay. And that's our backbone. And of course, the second solution is more efficient solution is satellite-based. So I'm not going to, Chen already told introduced it last year, no, the day before yesterday, and also I think last year there was our introduction on that. And so that's the roadmap for the large scale quantum communication. So we use metropolitan network, we use fibers for metropolitan networks. We use backbone or repeater to connect the cities, and for some even long distance, and for all somewhere like abroad, so you don't have easy fiber access, you use the satellite. And actually now, yesterday, many of you already see the small telescope there. We can now do a really movable telescope. We just put it any, okay, embassy, or don't tell them, but in roof of the embassy, then just open it. We can use it to connect to the satellite. So that's how we developed in China. Basically, in 2006, we used the quiet state method. We exceeded 100 kilometers, and 2008 we start to build multiple nodes, and then. Further, we build the metropolitan networks and another metropolitan networks in Jinan, and then in 2014 we start to build our backbone. So go to the secure communication backbone. So it's from Beijing to Shanghai and across Jinan to Hefei. I mean, the direct distance from Beijing to Shanghai is 1,400 about, and because we have to pass Hefei, of course, because our university is there, and the total fiber distance is about 2,000 kilometers, and it takes like 42 months to make it. It contains 32 trustable relay nodes, 31 fibers, and we have existing metropolitan networks in Hefei and Jinan, so we build also in Shanghai and Beijing. And back then, the main customer was China Industrial Commercial Bank, the Xinhua News Agency, and China Banking Regulation Commission. And why first we select this? If you look at it, it has like 1/4 of the population of China and 1/3 of GDP. So that's after it was launched at 29th of September last year, and this is how the topology of the different cities. This was Hefei, this is Jinan, this is Shanghai, this is Beijing. If you look at it, all contains a loop connection and then star topologies. And in between what we did, so before we install to the real field, we built an indoor platform to test all the equipment. All devices are operated for 24/7 for the stability check for more than 6 months before install to the backbone. And actually this day is when we start to install the devices to the field. And the entire line, so we built actually 32 nodes and 31 fibers really at a big room, but not here in Hefei. But if you realize, here is 61 quantum links because Ten Yun borrowed 1 pair of the quantum device and never gave us back. And so that for the first, we only have 61 pair of devices because originally it should be 62. And in 100 86 total sets of quantity. It's about half of the devices we finally used. And now we have also installed a 3+2 test bed permanently in Hefei, which is it's like a simulate 3 main city and 2 relays. And then in the future, actually, all the devices before installing will be tested here for like also we will test the security test, the standard security, also all other like side channel test, also the here because we don't use the measurement device independent method, so we will also check this. We use classical ways to check whether if there's some problem with the devices. And then to install, then the people works very hard. Actually, it's very quickly. I think like 2 months, it was the first set was installed, and this is yesterday when you visit us. And here here is at Hefei Control Center, and we can do with our backbone. We can also together with satellite. So this meeting room is actually at the Urumqi, the Nansan station. So it will use the backbone, and together with the Mrs. quantum satellite, the key created by the satellite, and it encrypt. So yeah, this again is the topology of the left side is Shanghai, and the right side is Beijing. And this is the key rate of 2017, and we did a optimization at June, so you can see it was encrypted a lot. So initially, I mean, so the channel loss was not as before as the company told us. So and we optimized the topology a little bit, actually quite a lot, and then we get like the minimum key rate is about 25 kilobyte per second. So this is a typical application, which I think yesterday, I assume you already see it. So we have in the industrial and commercial bank, it has 3 data centers, 1 in Beijing, 2 in Shanghai. So as I said, they couldn't update their key once a year sometimes. Now we do delete 10 times a minute, and the encrypted data is about 100 megabytes per second. And this is now the expanded users for the actually selected users for the backbone. So we have like a bunch of banks. I don't want to read it, but many the data running there is banking regulatory information, also cross-border payment information, management of the Chinese yuan, and also the backup of the disaster recovery, key distribution for the system maintenance, and real-time transfer, online transfer, this kind of thing. And also not only banks, we also have then the fund, and also the securities can also come in. And the next big group of the user is the state grid of China. You know, once if this company was controlled, basically the whole country will be down, basically. So it also has like backup for disaster recovery, development system, general grid, load storage, optimal operation system are running, working there. Actually, also there some banks are start to really thinking whether it's possible to apply this to blockchain, for instance. And yeah, the satellite I will skip. But actually, I looked through the Jen's talk yesterday. I just want to mention 2 things. First of all, why it's called Mises. So the Mises is our philosopher, or oldest, actually the first scientist in China. He's about 400 years BC, and he really realized the first pinhole imaging experiment, demonstrating that the light travels in straight line. So people hear, then the image is reversed, and the pinhole experiment. And the Euclid, actually in Western, Euclid pointed out like 100 years later. And so yeah, this, I mean, I don't need to introduce the satellite itself. And also, why so it's not only because he's the first scientist, because also he's a really nice philosopher. he believed that we need a universal love and peace. And he also really proposed that Duan is the smallest unit which cannot be cut. 端体之无序而最前者也. It's about the same time as Domokuri's proposed atomic theory. And also, he proposed that in the absence of the force, the movement does not stop. While actually in the meantime, Aristotle believed that the force was necessary to keep an object moving. And actually, he also, the third law, he also kind of, he sees that, but I didn't find the original sentence, like this kind of Chinese sentence, but there's some story that he saw that a guy the guy on the boat, then he pushed the rope, and the boat will go to boarding. So he point out that so when you pull the rope also pulls you. So the third law also. And well, the second thing I want to mention is, so as you see, the payload of the satellite is like 500 kilograms. It's huge. But actually, 1 month or 29 days later, the missiles was launched. We also launched a payload together with Tiangong-2 and to the Tiangong-2 Space Lab. And there we have a small payload. Total weight is 58 kilograms and at very low power. And this we want to use it. Now we have designed for less than 20 kilograms. Hopefully in the future we can carry the payload on the navigation system. For instance, the Beidou navigation system, or in Europe the Galileo satellite, or in state GPS system. So, but for that, because we know that it has to go to the higher orbit. So there's already another satellite was approved. So we have the 3 phases. First phase, it's elliptical orbit at the shorter distance, 1,000 kilometer, and the long distance, 10,000 kilometer. And then this will run for like half a year, and slowly it climbs up and go to the 20,000 kilometers, the second phase, and finally it will go to the geostationary orbit. Select one point and stay there. So this was approved, and this takes like 3 years to there, probably, I think. And they claim that we were still thinking that whether put some more energy there to even late after the experiment, even climb up to the Lagrange point. But this was not decided. And but this satellite not only for quantum communication, we also will put a cold atom experiment there we can measure the gravitational redshift, for instance. And also for the standardization at ISO and IEC working group meeting last year, that's November in Berlin, we have a project approved security requirement test evaluation and method for QKD. It's not proposed, it's actually approved, and we want to do a lot of things. And so if you go back to look at the growth of internet, the internet actually becomes as an experiment in computer science by support of the Defense Department back to 1960s. And then in 1970s, basically all the university has the point-to-point network connected. And so only at 1988, the NSFNet proposed supported the backbone project from the west to east. And after that, like 15% per year increased, and in 1995, it became like this, and then Net quit and a company take over. And actually what we want to do is similar. So I mean, we have now, so this looks like, this is the data center of banks. These are the data center of the Ali Yun, and also the to be built, and also we have the supercomputer centers, and we want really have these different lines. Actually, now this line was already done from Hefei to Wuhan, and these 2 lines are already approved, so it will start to build this year, and actually, but this now is not operated by the university, but the company took over. So if you are look outside, the CAS quantum network company will take care of the building this network. And also in global, we know that Europe, Vienna group also proposed a nice network, also Batella, but this one I think they are stopped somewhere. But still in UK, there's this network, and in South Korea also they're playing. I mean, in future, we really want to have this the platform that space ground integrated global quantum communication infrastructure. We want to infrastructure as service, to platform as service, to software as service. We want to really secure, quantum secure every bit in the internet. And this is the team. Jianwei is the chief scientist, and Chen is the chief engineer of the satellite. I'm the chief engineer of the backbone. Chen is chief engineer, the vice chief engineer of the backbone. And this is before I took over the backbone, and now you can see what I am now. So with this, I would like to thank you for your attention.
Okay, thanks for the nice talk. Any questions from the audience?
Oh, hi. Yeah, thanks for the talk. So in the intercity fiber-based communication, if you started to add more users end to it, I think the crosstalk might be high due to the Raman scattering, which may have a bad influence on the qubit. Have you got any solution to that?
No, actually, I don't think crosstalk is a problem. Actually, I didn't mention that the Beijing-Shanghai backbone was originally made with dark fibers, actually. But now we already have the technologies that it's even with bright fiber, you don't need to give me the whole fiber, just give me a wave with the WDM. You can already send the keys. So now what we can do, I really double checked quite many times with Chen. So like 80 kilometer fibers, single fiber, you start with distributed key, you can support 1 terabyte of encrypted data with only single fiber. So together with the data fibers, you don't need to build additional fiber for that. You can directly use the bright fiber. There's no crosstalk problem, I think.
Okay, thank you.
Okay, this question from Chen.
Very nice to talk. We also follow the last question. Actually, currently the fiber network is built up last 20 or 30 years. Would you think possibility we rebuild up the quantum network, or we use currently fiber network upgrade to quantum network? What's your comments? What's your opinion?
I didn't get to the last sentence, but yes, as I said, so we can use directly. I mean, there's really so many in China. I heard there's actually even like 10,000 kilometer fibers was not used actually. But we can. I think it's in the end we don't need to build new fibers. We just upgrade the relay stations. That's what we want to do in the future. So we will use existing telecommunication fibers, and only at a really extreme place, like for instance, we talk about with the state grid company. In their case, sometimes the smallest distance between the stations like 200-300 kilometers or even 400 kilometers. In this case, we might need to build the ultra low loss fibers newly there. But all the normal place, we don't need that. We don't need it. We just use the existing fiber network.
Okay, so for time being, let's thank you all again for the nice talk.